So today we will look into an important uh, problem, important idea, that is recursion. So in this context, uh, you know, uh, so what is recursion? Let's try to understand recursion through an example. So like the factorial function, right? So factorial n is 1 times, 2 times, so on and so forth till n. So this is one way of defining factorial n, and an alternate way of defining factorial n is factorial n is equal to uh, factorial n minus 1, factorial n minus 1 into n. And if we just say factorial n is equal to factorial n minus 1 into n, this wouldn't be sufficient. We should have the base case. That is, the base case is factorial 0 is equal to 1. So this is what is called as a recursive definition or recursive function, because we are defining the factorial of n by using factorial definition again. So this is recursive functions. Can you give me any other example of factorial recursive functions? Fibonacci, okay. How many of you studied uh, Fibonacci? Yeah, exponential, no? So exponential function is a good Ackermann function, okay. Even this function simple thing, so sum of first n numbers. So if you have some notation like Sn is equal to sigma I is equal to 1 to n I. So then, so what would be the recursive definition for this? Sn is equal to, yeah, very good. So Srinya. So is equal to n minus 1 plus n. This is a recursive definition, and the base case is S1 is equal to 1. Very good. So this is yet another example of a recursive definition. So many times what happens is thinking about some problems recursively makes it easier for us to solve them. Maybe for factorial and the two functions that we have seen, recursion may not be that necessary, but there are many cases where we see that recursion really comes handy. So now what we will do is we will, let me clear the screen. So we will write a program. We will write a program to compute the factorial of a number in a recursive fashion. All right. So Control N. Any kind of sequence can be recursive. Maybe, maybe not. Not necessarily. Fact dot C. All right. So studio.h and sorry. So here we are And then so we will have so we have a function, so we want to do printf so we want to write a function factorial. So yeah, so let's see. So now we have to define the factorial function. That's the story. So factorial is a function which takes as parameter a variable, which an argument which is of type integer, and it returns a value which, you know, the factorial of a number is always a positive number, right? So we can say that the value returned by factorial, it is of type unsigned integer because its value is always positive, unsigned integer. And then we know that if n is equal to 0, if n is equal to 0, what happens? We return 1. So otherwise, no, let's use another variable, unsigned int, fact10. We say fact10 is equal to n times factorial. So what is unsigned? So again, did you read the textbook, guys? If you read the textbook, you could have read about that unsigned int. If the value of that, if the values are always positive, then we declare that value to be of type unsigned int. If the values are always non-zero integer, non-negative integers, that is 0 or positive integers, then it is of type, then the value is of type unsigned int. Yeah, it doubles the range of int. Yeah, that's true. That's true. And then it returns fact. So the important thing here is, let's say if you call factorial function with factorial 5. So factorial 5, in order to evaluate factorial 5, on line number 10, factorial 5 calls factorial 4. And factorial 4, what it does is, in order to compute factorial 4, it calls factorial 3. Factorial 3 calls factorial 2, factorial 2 calls factorial 1, and factorial 1 calls factorial 0. And when in factorial 0 on line number 7, n turns out to be equal to 0, so it returns 1. So that is where the recursion ends. So let's run this program first and see what happens. So GCC minus G. Let me use /n. So it is 4. So it's all looking good, right? So are you all with me here on how this code works? Does it make sense? So now let's try to trace this code and see what's going on. So we get a deeper understanding. I'm putting a breakpoint on line number 22. So I'm going here to run and I'm saying toggle breakpoint. So there's a breakpoint on line number 22. So now let's start debugging. I'll say start debugging. Huh. Okay, there is a problem. So let's do one thing. There is no problem. Delete, remove all breakpoints. And so let's compile this. This is compiled with minus G only. No? So why is it a problem? Okay, let's try again. On line number 22, we have the breakpoint. Toggle breakpoint. Restart debugging. Yeah. So the value it is asking for value of n. Let's say the value of n we enter as 4. So now we are on line number 22, and we will do this step into. So we will use this step into functionality to trace how the factorial function gets executed. So now can you tell me what is there on the call stack? Can you check the call stack? The call stack has the activation record associated with main, and in that activation record, there is the memory for the local variable n is allocated, and the value of the variable n is 4. So Sumant has this question, what is the difference between GCC minus G fact.c and GCC fact.c? So if you want to use GDB, you should use minus G. And I asked you guys to try out GDB once. Not once, more than once. You wrote so many programs. By this time, you should have used GDB and see how it is working. Did you try the GDB once, Sumant, at least? Yeah, you should try. I kind of, it's not a mandatory homework. When I introduced GDB, the first thing that I asked you to do is look at, the GDB cheat sheet and try to use few commands and trace your program. Can you, those of you who didn't do it yet, can you do it? It is a very, very powerful tool and you should learn how to use it. Okay. So the activation record has the call stack has the activation record associated with main, and in that activation record, the memory for the local variable n is allocated, and n holds the value 4. So now we are stepping into this code into factorial n. Now if you check the activation record, the call stack, the activation record for factorial with 4 as parameter is pushed onto the call stack. And factorial with 4 as the parameter, it has the local variable n and fact n. And this local variable n has the value 4. This is the argument actually. And the fact n's value is equal to 0. It can be any random value, but right now it turned out to be equal to 0. So in order to draw this, I would like to draw this picture and explain what's going on again. So this is the activation record for main, and the activation record for main has the memory for the local variable 4, for the local variable n, and its value is equal to 4. And then this is the activation record for, what do I say, for factorial with invocation. So right now, so main is called with the fact4. This is the activation record for fact4, and so here n has the value 4. Since we are calling, so here I want to highlight in main, we are calling factorial with value 4. And this value 4 is copied into the memory location associated with the variable n in the factorial. Okay, so this is equal to, so this value 4 is copied there. This is equal to 4. And then there is local variable factor. This is the state of the call stack. This is the state of the call stack. Are you all with me here? Does it make sense? And there is no relationship between this n and this n. And this particular approach where the value is being copied, the value, the argument that we are passing is copied, that parameter passing mechanism is what is called as a call by value mechanism. Call by value parameter passing mechanism. Yeah, it doesn't matter whether we use k or whatever the variable in factorial, it doesn't matter. Okay. So here, it can be any variable. So let's say if you used variable k, let me use a different color. So it doesn't matter. It still works. So all I'm telling you is that when main calls factorial, main is calling factorial by passing the parameter value 4. This parameter value 4 is copied into the local variable. Like for example, this could be k, it doesn't matter. It can be anything. K is like a local variable for the factorial function, except that it is initialized with the value that of the argument. The value of the argument is 4. So 4 is copied into the memory location associated uh, with k. Okay, so earlier we used n, the variable n. It can be k or it can be anything. It doesn't matter. Are you all with me here? Does it make sense? Great. So now let's keep going. So the value of n right now, if you see it, is equal to 4. And so this condition turns out to be false. You go to statement 10 and you step into it. And when you step into it, you can see that factorial 4 has called factorial 3. And this is what is there on the top of the stack. Factorial 4 called factorial 3. Focus on what I'm telling guys. There's an important concept. Don't get bogged down by the syntactic details. I'll take other questions. Are you all with me here that why now there are two different activations of fact are enabled. One is fact 4 and one is fact 3. Both are simultaneously active. So, and if you go and see here, this activation record, so you will see, no, you will have n is equal to 3 and you have different fact. So this is associated with this activation record is associated with the calling of the factorial function with 3 as parameter, and this is associated with calling of the function fact with 4 as parameter. So you can see that, so now let's get back here. Let me put it. So great. Yeah, this is an. So you can see, so how things are stacked up here. This is the call stack. And this one, this n and this n and this n, they are different. This is for main, the local variable n in main and the local variable n in the activation associated with fact 4 and the local variable n in the local variable associated with fact 3. They are all distinct from each other and they don't share anything with each other. Okay, each one has their own memory. Are you all with me here till this point? Doing all right? Good. So now let's keep going. So now if you can see, factorial 3 has called factorial 2. Factorial 3 has called factorial 2. And so you can see that there are 3 factorial functions on the call stack. This corresponds to fact 4, fact 3, and fact 2. And then we go again. So now fact 2 calls fact 1. Fact 2 calls fact 1. Yeah, and fact 1 calls fact 0. So this is the depth of the recursion stack. So you can see that if we call fact with n, the depth of the recursion stack will be n. The depth of the recursion stack will be n. You can see there are 5 different versions of the variable n sitting on the stack. So now if you see in fact 0, if n is equal to 0, so what happens? The condition turns out to be true, and this return statement gets executed. And when this return statement gets executed, so fact 0 returns, let me use a different color, fact 0 returns 0 back to the fact n. Great. So, and then once 0, oh, sorry, 1, 1, sorry. Thank you. Fact 0 returns 1. And you can see in the call stack, the what is there, once you are out of the fact 0, the activation record associated with fact 0 is popped. So what is there on the top of the stack, of the call stack, is the activation record associated with fact n. And fact 1, it takes 1 and it multiplies it with 1, and it returns 1 back to fact 2. All right. So this is what happens. So now you can see that, yeah. So you can see now fact 1, fact 2, their activation, fact 1, fact 0 activation records are popped. And what is there on the top of the stack is the activation record associated with fact 2. And so it takes 1 and multiplies it with 2 and returns 2. So similarly, fact 3, what it will do is it takes the value 2 from here, and multiplies it by 3. So it generates 6, and 6 gets propagated upwards. And then again, what fact 4 will do is it takes 4 times 6. That's what it will do. This is the 6 value. It will take 6 times 4, and then this value will be propagated up back to 24. And main will print it. No, you got it completely wrong, Jaishnav. So it's not declared. It's only declared once or defined once. We are using the same thing again and again and again and again. So it's not declared again. So as you see that as we keep progressing, that now what is there on the top of the right now we are in fact 3, and fact 3 returns 6, and now we are in fact 4. Fact 4 takes the value 6 returned by fact 3 and multiplies it by 4, and it returns 24 to main, and it gets printed. So what is redeclaration, Harish? If you think about it, so redeclaration happens if the same function is declared again. Calling a function again is not the same as declaring that function. So there's a difference between function declaration, definition, and calling a function. So it is possible for us to call the same function again and again and again. So there is no problem. There is no error there at all. How many of you understood the whole stuff, the whole picture, what is going on? If we didn't use unsigned int and also if we didn't use return 1, so it's very good. So many times on line number 7, we are using if n is equal to 0, we are going to return 1. So many times what happens is if the termination condition is not right, then the stack keeps growing and we don't terminate. For example, let's do one thing. So if I run this program and if I enter -1, what happens here? If I enter -1 as input, what happens? See, it keeps on going and at some point it gives a segmentation fault. Let's take this simple example. If you didn't understand, oh, unsigned. Yeah, it takes -1, but good question, good catch. No, we are passing this. We are checking if n is equal to n is integer, right? So don't worry about it. So let's. There is this question: how does fact 0 work? What happens when we call fact 0? It cannot return a negative number, but will. So what is fact 0? How does it work? Can you tell me the trace of the program when we call it with fact 0? So when we call factorial with 0, so we check if n is equal to 0 and we return. Yes or no? Does this make sense? Someone asked how this whole thing works. So execution of fact 0 is very simple. But let's say if you call fact 1, how does fact 1 work? When we call fact 1, what happens is, what it does is it does 1 times factorial 0 gets called. But we know how to compute factorial 0, right? So factorial 0 returns 1. So because of that, 1 times 1 is 1. So and we can see how fact 1 works. Yes or no? And if you call factorial with 2, then you call 2 times factorial 1. And if you kind of see recurse, this is where the recursive thinking comes into picture. The way to compute factorial 1 is, it is 1 times factorial 0, but factorial 0 is very simple because if n is equal to 0, you return 1. So the story is all kind of adds up. So this is how the computation proceeds. Are you all with me here, guys? Does it make sense? Yes, no, maybe? So here so let's see what is the time required, what is the space required for this to compute factorial in this program. What is the space? Not exactly, approximately. Is it proportional to n, or is it proportional to n square, or is it proportional, is it constant? What is it? What is the space required? So before you answer this question, let's try to write a different program so that we can compare and contrast these two programs. So Yeah, so I will so control S. So we would like to write the factorial program in a using a loop fashion. So what do we do? So for I is equal to 1, I less than or equal to n, I is equal to I plus 1, and what we do is fact 10 is equal to fact 10 star I, making time. So are you with me here? Does this code work? Does this code compute the factorial of a number? Does this code compute the factorial of a number? So let's compile this code and see what happens. GCC minus G fact loop dot C. So if you see 5, you get factorial. So here you can see we are able to compute factorial n in two different ways. So we are computing factorial in two different ways. One is an iterative version, the other is a recursive version. So these are two different, this is a different, in a different file I did this. It's factloop.c and this is fact.c. So in fact, here we are using recursion and here we are using an iterative version. So if you look at the operation complexity, like, or let's say maybe approximately what is called as a time complexity, how many number of no, it works even for fact 0 also works. It's not a flaw. If n is equal to 0 as a parameter in this loop, what happens? You never enter the for loop. And on line number 10, you return fact 10, but fact 10 anyway is equal to 1. So it still works. It's not an issue. So what is the time complexity for the iterative version and for the recursive version approximately? It's approximately proportional to n. You do n multiplications here. In recursive version also, you do n multiplications. But how about space? What is the space complexity? How much space is required in the iterative version and in the recursive version? Good. So in the case of iterative version, you can see the memory required is constant. So fact requires some 4 bytes, I requires some 4 bytes, and maybe n requires some 4 bytes. So overall, you can kind of get away with 12 bytes. It is independent of n. No matter what n is, it will be the same. But in the recursive version, there is a stack, right? So what happens is you don't explicitly see it, but you implicitly it is there. Fact n calls fact n minus 1, and fact n minus 1 calls fact n minus 2, so on and so forth. So there is a recursion stack. There is a lot of memory that needs to be allocated on the call stack, and the memory required is proportional to n. And this n corresponds to the depth of the call stack. It's okay, n plus 1, it's all right. We are just trying to get a big picture. In the big picture of things, n and n plus 1 doesn't matter. Okay, so in this particular case, for computing factorial using recursion is using recursion is a overkill. So how 12 bytes? There are in the iterative version, there are 3 variables, right? Fact n, I, and the argument n. If you add them together, it will be 12. 4 plus 4 plus 4. 12. Hello. Can you all hear me? There is some problem on the Zoom from my side, and because of that, I got into this issue. And before I left, I made someone, in order to set things up, I made Akash host. I'll make myself. Anyway, I think it's all right. Yeah. Akash Gorla. Hey, Akash, don't get surprised that you became a host. Yeah. Good. Let me share my screen again. Because I made you the host, Akash, because there is some problem, and if I exit without making someone host, then everyone will be logged out. So you are there in the tops. I made you the host and logged out and came back again. Good. So that's about recursion. So the important point here is in recursion, the problem that factorial n is a simple problem, and so recording is still going on, if I'm right. Yeah, recording is still going on. So good. So yeah, so factorial is a small problem, and you may not really need recursion, but there are some problems where recursion really comes in handy. So in this context, I would like to share with you the one problem. Apparently, in the last office hours of mine, so one of you asked this nice question, and it seems it came up in the discussion in one of the TA hours. So the problem is on, so like there is one problem where you have this denomination $20 bill, $10 bill, $5 bill, and $1 bill. And so you want to, so given n, you want to express this n in terms of these denominations such that we minimize the number of denominations. So the number of coins that we use. Like for example, if n is equal to 30, So we can express 30 as $20 plus $10. And the approach given in the textbook, which you have coded up, is try to use as many $20 bills as possible, and then you try with the next highest possible denomination, and so on and so forth. This is what is called as a greedy approach. And then, but it seems there is a, let's say instead of $20 bill, if we have $26, $10, $5, and $1, and if you take $30, $30, if you use the same approach, you use one $26 bill plus four $1 bills. But then there is an alternate way to do it, that is like for 3 into $10, where you just use 3 coins, but whereas here you are using 5 coins, that is 4 $1 bills and one $26 bill. So the greedy approach doesn't work here. Greedy is you just try to greedily exhaust. No, you want to use $20 bills as much as you could, and then after that you go to $10 bill, and you use as many $10 notes as possible, so on and so forth. That is the greedy approach. If you apply the same greedy approach, it doesn't work. So the challenge problem for you, because this is the challenge problem. So given denominations d1, d2, dk. So here, like for example, d1 is this, d2 is this, d3 is this, d4 is this. Given denominations d1 to dk, so we would like to express a amount n using sigma I is equal to 1 to k xi times di. We want to express n using some of these. And what is the goal? So the goal is such that sigma xi, such that sigma xi I is equal to 1 to k is minimized. So this is the challenge problem. I want you to come up with an algorithm for this and write a program for this. So this is the challenge problem for you, which I would like you to try over this weekend. You understood the challenge problem? So if you think about this problem recursively, then it becomes easy. That's the reason. No, it's not, they can be anything. Okay, but you can even try to solve it even for 26, 10, 5, 1. But you can take from the user the input that d1 to dk. Now tell me what is there to repeat. The problem is you are given k denominations as input. It can be anything. So the user will, in one case, the user may say 20, 10, 5, 1. In another case, the user may give 26, 10, 2, 5, 1, so on and so forth. It can be any denomination the user can give. And then he'll also give an amount. So $100 or $150 or $151. And you have to express, you have to minimize the number of notes. That's all. Devesh got it right. So you want to express, you want to give it, so you want to minimize the number of notes. Are you all with me on the problem? Did you understand the problem? Yes, no? So here, if you think about this problem recursively, it helps. That's the reason. Yeah, the user should input the denominations and the amount. That's true. Good. So now, uh, so we will move on, and I want to, in the last 15 minutes of today's lecture, I want to introduce a new idea. So, so what happens is in practice, so if you see, let's take a small program. Uh, oh, you are not able to see the screen, I will share it with you. I forgot to share. Dots. Hurry, again my Zoom has got into some problem or what? Okay. I think I'm good. Yeah. Now can you see the screen? Thank you, Anirudh, for clarifying. See, guys, when I ask a question, like there is a main idea behind that question. You are all in the other section also, when I posed this challenge problem, they are all trivial questions like whether we have 4 denominations or 5 denominations, or whether I should take the input, and how should I mail the code if I get, all these things, these are all frivolous questions. There's a main idea behind this question, and you should learn to focus on when something is being discussed and when a problem is being posed. What is the core of the question is what you should learn to focus on. All other things, so that tells you where you stand also. Okay, so that's what you should learn. So you're all uh, uh, you could be learning things you could have been learning things in a certain mode till now, but now you are on your own. So when a problem is posed, you should go to the crux of the problem and focus on it. The rest is all details. The details we can figure out anytime. So here, let's go back to basics in the last 10 minutes. So we'll have some fun, interesting things we will do. So this loop.c, it is there. Where is it residing? It is residing on my hard disk. It's residing on the file system, right? And so when I compile this program, so let's compile this program. So gcc loop.c -o loop. So where is the executable present? Is the program is being run or not, or what? Where is the program present? So we have, it's not run. So you can see if I do an ls, you can see here, you can see loop.c source code program is present on the hard disk, and loop is an executable. So it's in green color, that green coded, and it is also present on the hard disk. The program is not up for execution. So if I do a htop, in my machine, there are 6 cores, and you can see, yeah, so it shows how busy my different processors are. The maximum utilization of any core on my machine, in my processor, is at most 30 to 40%. That is how it is like. And if you see the memory utilization is some 4.7 GB out of 64 GB memory I have. Let me do one thing. So I will use screen. Okay, htop. This is on terminal 0, I am running htop. And on terminal 1, and I am running loop. So once I start running loop, you can see the, that core 2 is busy executing loop. because the loop program, it doesn't do anything. It just keeps iterating fast, very fast. It keeps iterating. So it is completely hogging one of the cores on my machine. So when we give a program for execution, that program will get say process ID. If you see here, the process ID for loop, the process ID for the loop, it is where is my loop? It is 5078. Let me clear my drawing and let's go back here. Every process, once it becomes active, it becomes a, so if I do ps minus aef grep loop, yeah, you can see the process, every process, it will have what is called as a process ID. And you can see that 5078, this is the process ID associated with the loop. And now I would like to run one more instance of loop. Just like it is possible for us to have multiple loops, multiple Chrome browsers, we can have multiple loops. So now if I go and see now, you can see the core 3 and core 4 are completely hogged, and one process associated, there are two different processes associated with the same loop, and each of these processes, they are occupying one of the cores, each one core. So if we go and see ps minus aef grep loop, you can see there is one process with the process ID 5078, 5078. So check this, and there is another process 5279 associated, which got created from the same executable file that is present on the hard disk. So an important idea here is, and in general, there are many processes that are running on the system. So what happens is in your system, there is certain amount of physical memory that is present. Like on my machine, 64 GB of memory is present. So this is physical RAM. But what happens is, let's say, so from loop, there are two processes that got created. This is the memory map. This is what is called as a virtual memory map. Let's call it as, for every process that is executing, there is what is called as a virtual memory map. Just want to double check you are all able to hear me, right? Okay. So for every process that is executing, there is what is called as a virtual memory map. Like for example, for the process 5078 associated with one loop, I'm using VMM as a shorthand for virtual memory map. This could be the virtual memory map for the process 5279, which is associated with the same loop, or it could be for any process. For every process, there is what is called as a virtual memory map. This is not like real memory. It is just an abstract view. And what happens is each of this virtual memory, it is divided into pages. So these are all pages. These pages. And if you see this, like for example, the size of the virtual memory map associated with a process, it could be 4 GB. It's a logical thing. It is not really that 4 GB of memory is allocated. Because if you see the loop program, all we are using is just one variable I, and that variable I is a local variable. It's present in the function main. So the memory required by the loop program, it could be extremely small. Like for example, if I am right, maybe let's see what is happening. If you go here, the memory required by loop program, it is something like 4 MB, something like 4.376 or 5 MB of memory is required. 5 MB of memory is required. And yeah, so if you go back here, sorry, not here. here only, A4 or A3. Yeah. So similarly here, this process also has memory map. This is a virtual memory map. But what happens is there's a physical page, your memory, it is divided into physical pages. This is also logical division of pages. But what happens is a virtual memory page here gets mapped to a physical memory page here. A virtual memory page here, it gets mapped to a physical memory page. So out of all the pages that are active, that are there, logical pages that are there, only some of them could be active. This and this and this could be active because the size of the program is small. Similarly, for some other process, this page and this page and this page, these three pages could be active. So for all the active pages, what happens is a physical page is allocated. A physical page is allocated, and for this could be allocated. So the good thing about when we write programs is, when we write programs, we don't need to worry that our programs are coexisting. When we run the programs, the associated processes are coexisting with other processes. We don't need to worry about it. Because if we kind of worry about, if that's not because of this idea of what is called as a virtual memory, you just think that everything is available for you. And this mapping of virtual memory pages to physical pages, it is done by a combination of your CPU. There is what is called as a memory management unit in your CPU plus operating system. Both together helps in mapping your virtual memory pages to physical memory pages. CPU plus OS. Specifically in CPU, there is what is called as an MMU, memory management unit. The memory management unit along with OS, they together map your virtual memory pages to physical pages. So because of this, when you write your C programs, or you write, we don't need to worry about the fact that on your system there are many processes that are running, and you are sharing the memory, available physical memory, with other processes that are running on the system. You don't need to worry about it. So now, like for example, here, let's go back to the thing here. Let's try to print the address, or yeah. So let's do this. Printf, no, address of, let me, yeah. So the inactive virtual pages aren't mapped to the physical until they become active. Excellent, Rahul. So can they become active and inactive whenever they want? They can become active. Inactive, they become by not referring to those pages. Okay, so are you all with me here? If you're all with me, then I will show. Yeah, I want to, can I clear the screen if you're all with me here on this particular thing? Let me clear the screen because I want to show you something. So Control N, hash. So now I'm just printing the address of variable n here. So the question for you is, the address that is being printed, what is that address? Is it a physical address or is it a virtual address? The address of the variable. The address of the variable that is printed, it is always virtual address. You will never get to know the physical address because the operating system, without the knowledge of the programmer, maps the virtual addresses to some physical addresses. And as your process keeps executing, sometimes this mapping also keeps changing. Like sometimes a new physical page could be allocated for a given virtual page. So because of that, you will never know the real physical address the of anything in your program, of any variables that you are using in the program. You will never get to know the physical address. You will only get to know the virtual address. Are you all with me here? Does it make sense? What code is there? There's nothing. There's no code here, Anjali. It's very simple. All we are saying is, the addresses that you see in your program, they are not the real addresses because so if this is your process, if this is, let's say for a particular process, this is your process, a virtual page here, let's say variable n is present in this virtual page, and this is your physical memory, and this is, so this is your virtual memory layout, virtual memory layout, and this is your physical memory. So what happens is when the address that you get is address, this virtual address, this physical memory address you will never get to know, because sometime depending upon the circumstances as your program executes, this mapping could change, and maybe your operating system and CPU can migrate this page, can copy this page to a different page in the physical memory and change the mapping function internally, and all of this happens without you knowing at all, knowing any of these details at all. So the mapping can change from this to this. So the physical memory associated with a variable can change, but the virtual memory associated, what do you say? But the virtual memory address is going to remain the same. Are you all with me on this one, on this particular idea? So the two ideas that you have seen in today's class, they are very important. This idea of, you will study a lot about this in your operating systems course, but this much understanding is necessary for you so that you know what is happening under the hood when you execute your programs. We can never find the physical address. So what do you mean by virtual memory changing? The virtual address can change for a different reason. When you execute, it's not going to change. Like for example, once the address of the variable n is fixed, it is not going to change. The address of the variable n in main, once it is fixed, it's not going to change. Rahul Garg. So you are EC students. CHT, everyone will have operating systems. It will be there, Rahul. For ECS students, I don't know. No, it's not going to, the value 4 is assigned to the memory location associated with them. So whether it is equal to 4 or 40,000 or 4 million, it's not going to change. All right. So shall we take a break here for today? So if you're all fine with today's lecture. So two important ideas. One idea is recursion. I want you to understand this idea of call stack and how activation records are pushed and popped, and how different activations of the same function are simultaneously active. That is, fact 4 and fact 3 are simultaneously active. And the next important idea is virtual memory. That every process, when you give a process for execution, it becomes a, when you give a program for execution, it becomes a process. It becomes a process, and every process has a virtual memory of its own, and this virtual memory gets mapped to physical memory, but we don't need to worry about this mapping because the operating system and CPU will take care of it by itself in a transparent way without you uh, worrying about it. So Adarva says that he don't understand the difference between iteration and recursion. Adarva, I would like you to watch the video lecture again, write the code, and uh, see and check whether it makes sense to you or not. And then, of course, we can get the clarification from TAs or from me later. Virtual memory is also, see, as someone Rahul, I think, pointed out, see, some part of your virtual memory may not be active at all because your program is small and you don't need that part of the virtual memory. That part of the virtual memory is never allocated any physical page. What do you mean by, Hariharan, what do you mean by difference between RAM and virtual memory present in the hard drive? Where does RAM and virtual memory will be present on the hard drive? I don't get you at all. No, where is virtual memory present in a hard drive? Oh, when it's not allocated any physical page, then how can it be accessed later? It's a good question. There are multiple ways of doing it. One way of, there is something called as a swap space, and other is from the executable file from which it is created, it will be brought in. Like for example, let's say if you are using Microsoft Office, no, or Microsoft PowerPoint. How many of you use PPTs? PowerPoint presentation. You will see there's a huge software with large number of features. So like most of us, we use maybe 10% or 20% of the features. So what happens is, the code associated with these 20% of the features, uh, they will be active and they will be assigned physical pages. But when you use a feature which is not used before, the code associated, the instructions associated with that feature should have to be brought from the hard disk to the memory. So what happens is your PPT file, executable file, it contains that code for the unused feature before, and when you touch those pages, then what happens is they will be brought into the memory, and they will be assigned physical pages, for example. Does it make sense? Kind of approximately. That's true. When the code runs, then physical pages will be allocated. It's an approximate view, but that's a good view to have. Good enough view to have. All right, so I will stop here today's lecture.